Welcome to the fifth presentation in a series on drill string and drilling dynamics. This one devoted to what happens if you put a positive displacement motor, a PDM, in the drill string. This talk builds on what was discussed in the fourth talk on fluid dynamics, but the dynamics with a motor is much richer as it couples the fluid dynamics with drill string rotation, perhaps surprisingly axial motion. An outline of what you will learn. Firstly, what positive displacement motors are and how they couple the three propagating modes in the drill string: fluid, rotational, and axial motion. Then we will see how what you measure at the surface is not exactly what is happening downhole. And I will describe how motors can amplify axial waves and briefly describe a lumped bit motor model that builds on the bit model in the third talk. Finally, we will get to the important subject of high-frequency rotational oscillations when there are tubulars below the motor. Positive displacement motors, often known by their acronym of PDM. What are they? They are also known as Moineau motors, after their inventor, René Moineau. There is a rigid, lobed motor in a helical spiral, rotating inside an elastomer-lined helical stator that has one more lobe. Moineau's original invention was actually a pump, with rotation driving flow rather than vice versa, but the operating principle is the same. Pumping fluid through generates rotation in the rotor. Rotation speed is proportional to the flow rate, unlike a turbine. In drilling applications, the stator is attached to the drill string, the rotor is attached to the bit, so the drill bit rotates at the sum of the motor rotation speed and the drill string rotation speed. Before the advent of rotary steerable systems, nearly 30 years ago, they were the only way of reliably steering a well. If the motor has a small bend, so the bit rotation is at a small fixed angle to the drill string, then by orienting the bend correctly, the bit will generate a section of a curve. If the drill string is rotated at the same time, then the bit drills a straight hole, or at least one whose trajectory is determined by gravity alone, which is slightly overgauged due to the bend. So by appropriately alternating periods of rotation and non-rotation, i.e. sliding, a desired trajectory can be followed. Nowadays, motors are also used straight and with rotary steerable systems in order to increase the power available at the bit. The model we shall use for them is quite simple. The pressure drop across the motor is proportional to the torque below the motor, and the rotation speed is proportional to the flow rate. Torque proportional to pressure is a very good approximation, up until close to stall pressure. Whereas there is some drop-off in rotation speed with pressure as a fixed flow rate, as more fluid leaks across the elastomer. In the last presentation, we looked at how acoustic sources near the bit behave at late times. And a drilling motor with changing load, i.e. changing torque, acts as an acoustic source. At late times, the effect of the fluid above the motor can be approximated as a lumped compliance. We saw how the changes in pressure drop across the motor lead to changes in downhole flow rate, which reduce the bit pressure drop. The effect of this is that at late times, the whole system looks like a low-pass filter. But what happens at early times? At early times, we can ignore the surface boundary condition and simply regard the fluid in the pipe as an acoustic waveguide, where the outgoing pressure and flow rate changes are connected by the impedance. The motor pressure drop change causes a flow rate change, the effects of which head off to the surface, but for a short time we do not see any reflective wave. Matching the outgoing radiation condition and the bit pressure drop condition gives a simple quadratic equation that links the change in flow rate with the pressure change across the motor, the pressure drop across the bit at full flow, and the acoustic impedance of the fluid in the pipe. It's a quadratic equation, but we can linearize to get a feel for how much the downhole flow rate changes. Normally, the first term in the denominator, ZQ, is smaller than the bit pressure drop. So if the pressure drop across the motor changes by a substantial proportion of the bit pressure drop, so will the downhole flow rate. Remember, this happens immediately. It's an early time effect. And this reduction in the flow rate and the pressure drop through the bit means that the pressure change above the motor is less than the change in pressure drop across the motor. As we shall see, it can be substantially less. For a motor, any transient effects are going to be early time only, so the pressure spikes from a short-lived torque change are early time only, and what you see at surface is nowhere near as big as the effect downhole. All these effects are greater with oil-based mud because it is more compliant. Let's look at a simulation. This is the change in downhole pressure drop across the motor generated by a short-lived increase in bit torque. I haven't plotted the torque increase, but it was a sudden increase at 0 seconds, and then going back down again a few seconds later. The change in pressure across the motor is about 400 psi. This is what you see above the motor. The pressure spike is much lower, about 150 psi, because as well as the pressure going up above the motor, the pressure below the motor goes down. You could also clearly see the long tail from the low-pass filter. This is what the downhole flow looks like. The flow rate drops very substantially, about 40%. And then, when the torque drops again, the stored fluid is all released. There is also going to be stored energy in the drill string, so the combination of the two means that during the release phase, the drill bit will spin much faster. This also happens if the bit is lifted straight off bottom at the end of a stand without allowing a drill off. All the stored rotational and fluid energy is released very fast. The drill bit spins fast off bottom, which can knock lumps out of the borehole wall, especially if there is a bent sub. And the nozzles in the bit and the RSS will get extra wear from the very high flow rates. So what can we conclude about spikes in pressure that we see when drilling with motors? Firstly, the full change in pressure drop across the motor will not be seen above the motor. The spikes are simply too short for that to be true. The reason you don't see the full pressure drop is that the transient effect involves the pressure going down below the motor as well as increasing above it. The flow rate through the motor goes down, often significantly. One of the most important consequences of this is that the pressure at which the motor stalls also goes down. So the flow is lower than the surface flow. The pressure across the motor is higher than it seems from the surface data. So if you're looking at the motor characteristics, measured in a dynamometer in a laboratory, it will appear to stall much more easily. Also, oil-based mud is much more compliant, and the effects are larger. The measurement while drilling system can also cause problems with motors. There is a tendency to make the pressure pulses as big as possible when running an MWD system, as this makes the signal easy to detect at surface. However, if you have a huge increase in pressure when the MWD valve shuts, you will also have a very substantial drop in flow through the motor, and this makes it much more likely that the motor will stall. Up until now, I haven't mentioned axial effects, but the pressure couples directly with axial waves, as we saw for the fluid and axial waves via tool joints. The problem is that there is a feedback loop. If the bit torque increases, then the pressure above the motor increases, which increases the downward force on the bit, which increases the torque. We can quantify this using the coefficients that link the motor pressure drop with the torque, the area of the fluid above the motor, and the proportionality between bit torque and weight. And because of the feedback, it's a geometric series, which means that if alpha A over beta is close to 1, then there can be huge amplification. Now we have to think about how long these effects last. By Archimedes' principle, we know that a pressure rise can only give a transient weight change. After a sufficiently long time, the pressure rise above the motor reaches the surface and generates an equal and opposite upwards force, which travels back down the drill string as an axial wave. But that will normally be seconds later, so vibrations of a wide range of frequencies will be amplified. In particular, it means that running aggressive bits with low torque motors can lead to much higher levels of torque fluctuation. Remember, it's the pressure above the motor that matters, not the pressure drop across the motor. So the effects I talked about earlier actually help here. We can combine a motor model with a bit model to see what happens when an axial, rotational or fluid wave comes down the drill pipe, and compare that with just a bit model. Now the motor is an extended object, so this model won't be true at very high frequencies, but you need to get up to 50 Hz before the motor is going to be half wavelength scale, even for fluid waves, so it does have some validity. We can decompose the rotational and axial motion as before into forward and backward going parts. And we also do the same for the fluid motion. There's an extra constant here, the fluid impedance. Now, the bit equation. The torque equation includes both the drill string rotation speed and the motor rotation speed. And the weight equation has to include the extra pressure above the motor, 2 extra components. Finally, the motor rotation speed is related to the flow rate. I'm going to ignore the reduction in speed with torque, and the pressure is the sum of a motor term and the bit pressure drop. So another 2 constants appear here. So it's all quite complicated. I'm going to linearize it slightly, just the flow equation, so the pressure is linear in flow. When we do this, there is a quadratic equation as before to get the bit rotation speed, with the upper solution stable, the lower one unstable. There's 3 extra terms in the quadratic that come from different effects. The first one is obvious, an offset, because the motor is rotating as well as the drill string. Then we have a small effect because the pressure change affects the flow rate, which affects the motor rotation speed. This term is normally small. Finally, there is a term due to the effect we saw in the last slide, weight amplification due to pressure changes, and this effect can be very significant. If we linearize the whole thing and look again at the reflection coefficients for rotational and axial waves, we again get some quite complicated equations, which is worth looking at to see how things have changed from just having a reflection from the bit. For the rotational wave amplification, the numerator is unchanged, so it is still positive, but the denominator changes. The term due to the motor rotation increases it, but the other 2 terms tend to decrease it, so the amplification can be either bigger or smaller than without a motor. For the axial wave reflection coefficient, the denominator change is just as for the rotational waves. But there is an additional term in the numerator which always moves the system towards amplification, unsurprisingly, as this is from the weight, pressure, torque coupling. This means that for the right parameters there can be axial wave amplification. Now this approximation assumes that the motor and the bit are short on a wavelength scale, and the lowest frequency axial waves reflected back by the drill pipe have a wavelength of about 20 meters. But this analysis does indicate that there is a mechanism for axial wave amplification by the bit, and can certainly explain how there can be high levels of axial vibration during motor drilling with a PDC bit. Now let's get on to what happens with rotational oscillations when you have tubulars below a motor. In the last few years, these have become much more well known for the important reason that they are breaking a lot of downhole tools. Literally breaking. Shear failures of the steel from too many large amplitude stress-strain cycles. The steel is breaking at stresses that do not seem excessive, but when there are 200 cycles per second, that's nearly 700,000 an hour, so in a normal drilling run, there can be tens of millions of cycles. So why should there be tubulars below a motor? It happens when you're drilling with both a motor and a rotary steerable system. Why would you want to do this? If you can steer with a rotary steerable, why add a motor? The main use case is for performance drilling, trying to drill rock as fast as possible. It allows higher rotation speeds at the bit, and in particular is useful if the well is very curved at any points, as this reduces the maximum rotation speed possible for the drill string due to strain cycle effects. The other case is casing drilling. Normally, steel casing is run into hole after it has been drilled. There are different methods for doing both jobs at the same time, one of which is to drill with a BHA below a motor, which is mounted in the casing. After drilling, the BHA is removed using wireline. The BHA has to include underreamers to allow the casing down, and any steering, surveying or other tools, so it can be quite long. So why do we get strong, high-frequency rotational oscillations below motors? To get a strong acoustic resonance, you need a reflection coefficient close to or greater than 1 at the bit, which we know we have, and a reflection coefficient close to 1 somewhere above the bit. Also, sufficiently low loss between the two. The top reflection coefficient in this case is purely geometric. Everything rotating below the motor is attached to the rotor, and the rotor is thin. Here is a picture of some rotors on the right. Again, copyright Baker Hughes. Collars are fat. Rotational impedance is proportional to radius to the power 4, so there is a big impedance contrast. It's very similar to a free boundary. The reflection coefficient can be 0.95 or greater. We had some pretty good evidence that this is the right boundary condition from measurements made in a test well while casing drilling. This was done with quite a long assembly, and measurements of both torque and rotational acceleration. The resonances of the system could be simulated assuming different boundary conditions and compared with the measured data. There was a high level of vibration in the assembly, though no stick slip. There were multiple resonances, and they matched extremely well to a free boundary condition. As before, I'd like to show you some data, but I don't have permission. So instead, I have to point you to this paper again, where there are a number of illustrative data sections. I have created synthetic examples which show the same kind of behaviour as the real data. The paper contains a few more that I have not attempted to imitate, and I again encourage you to download it and examine them. Now let's look at some graphs that illustrate how the real data behaves. For this drilling assembly, the first below motor mode is at 192 Hz, which is where things are happening. The caveat is that due to the anti-alias filters, if the next mode were excited at close to 400 Hz, we might not see it. The blue line shows the filtered low-frequency rotation speed. Measurement is below the motor, so the blue line can be interpreted as the drill string in full low-frequency stick slip, with the motor rotating at a fairly constant average speed underneath it. The red line shows the 192 Hz amplitude, and you can see that it comes and goes. A lot of the time it tracks the low amplitude speed very well, which I interpret as being full stick slip, though at about 32 seconds it starts up and then goes away again. You can see that the system can go to and from full amplitude very fast, over about 10 seconds. This is later on in the same bit run, and is based on figure 13 from the Stavanger paper. The last graph showed minutes of data. This one is just 1 minute in total. Over hours of drilling, the system transitioned from the behaviour in the last slide, through continuous high amplitude, high frequency oscillations, to behaviour like this, where the bit is cyclically stopping at approximately the period of the rotational oscillation fundamental. Don't be confused by the fact that the blue and red lines have slightly different amplitudes, although the same shape. This is just my scaling. Where the two track in shape, we can be fairly sure that there is full high-frequency stick slip. Whereas with rotary high-frequency oscillations, they do not coexist with low-frequency stick slip. For sub-motor oscillations, they clearly do. And they stay full amplitude, even when the bit rotation speed is growing very fast. This behaviour carried on very like this for hours, with the motor still operating, which makes me fairly sure that it was rotating pretty much normally, even with the bit stopped. So it was turning the drill string backwards during the stationary periods. I've seen this in data above a motor, so I know it happens a lot. If the bit's not turning to the right and the motor is turning, then the tubulars above the motor are turning to the left. A lot of people at this point immediately think that this means there is a risk of them unscrewing, but that's not the case. If you have a nut and bolt to tighten it, you either turn the bolt to the right or the nut to the left. It's when the bit is going faster than the surface that you risk unscrewing. It looks like we have a pretty good theory to explain what is going on. There is a wave going up and down with a bit reflection that is slightly greater than 1, and a rotor reflection that is slightly less than 1. So with excitation, if the bit reflection exceeds the rotor reflection, then that resonance will grow. But we had hints that it was more complicated. The biggest one was some data during a downlink to a rotary steerable tool. The downlink consists of reducing the flow rate for a period of seconds and then increasing it again. This pattern of flow reduction pulses carries data very slowly. During each period when the flow was reduced, oscillations started growing and then died when the flow rate was increased again. A motor couples rotational, axial and acoustic modes, as does the bit. So while the rotational modes of the system are undoubtedly the most important factor, what happens if we include axial and fluid effects? If we look at the resonance as being a perturbed version of the purely rotational system, with the bit model and motor model we've used before, this comes out as the amplification factor. I will take you through it. On the left is the term from the simple rotational theory. The next term is one that's proportional to the bit torque over weight, gamma, the fluid area above the motor, A, and beta, the torque to weight pressure ratio for the motor. Inside, there are two terms. The first comes from a vibration going in one direction as a rotational wave and in the other direction as an axial wave. And this is the cause of the phase difference between the axial and rotational travel times at the resonance. It depends on the mode type and the relative wave speeds of the two waves. If the system is in the fundamental mode, then this is always going to be about 0.43, assuming everything is steel and there is not too much cross-section variation along the tubulars. Most importantly, 0.43 is positive, so this term is positive and makes the system more resonant. The second term comes from a wave that goes in one direction as a rotational wave and the other direction as a fluid acoustic wave. Capital sigma is a fluid impedance, and kQ bar is twice the bit pressure drop divided by the mean flow rate. I've written it like this, so it is obvious that it increases as the mean flow rate increases. The phase difference here depends on the wave speed in the fluid, but again will be positive for the first mode. This whole term is negative, so it makes the system less resonant. Importantly, it depends on the bit pressure drop, and hence the fluid flow rate. The term increases as the bit pressure drop increases, so this is consistent with the downlink data. The system must have just been on the edge of amplification, so that at the higher flow rate the system was not self-exciting, but with the reduced flow rate sections of the downlink, it was self-exciting. That's all quite complicated, but luckily there are some quite simple conclusions. There are four terms that determine whether the excitations will be unstable, i.e. self-exciting. Two of them change with drilling parameters, one with mean bit torque, so the drilling weight, the other with flow rate. Higher mean torque means reduced stability. Lower flow rate also reduces stability. There's a torque over pressure factor in there, so normally having a high torque motor, basically more lobes, increases stability. It's not in this formula, but the data hints that motor wear reduces stability. In the downlink case I told you about before, later on in the run when the flow rate was increased again, it took longer for the oscillations to die down. Having a higher bit pressure drop increases stability, whether it is from smaller nozzles or higher flow. And finally, things are generally worse in small hole sizes. That's it for the theory of PDMs and oscillations below motors. We'll come back to motors again in the next presentation, looking at stability of auto drillers using pressure control. Questions, comments, etc. to the email address on the lower right.